Hi, welcome to section 3.3, the remainder and factor theorems. So, we're going to basically do three things in this section, one of which I suspect you've all done before. Maybe you don't like it, but I would suspect you've done it before. And then another of which is going to be super important, and then finally we'll talk about the remainder and factor theorems. So the first thing that I suspect you've all done before is polynomial long division. So we'll get to an example of that here in just a minute. The second thing we'll cover is synthetic division, which is really slick and really fun, and I really like it. And then finally, we'll just talk very briefly about the remainder and factor theorems. Mostly, I'm going to wave my hands at them and tell you what they allow us to do, because they're super useful here with polynomials. All right, so you'll notice that on the board, I have a real basic, just numbers, long division problem. Like you probably learned to do, I don't know, third grade maybe? I don't know. I haven't taught elementary math, so I forget where exactly they do that. So you can see I have 7 into 341. I divide to get the 4 up top. 4 times 7 is 28. I subtract to get 6. Down comes the 1. And you repeat the process. Okay, I'm going to guess that I don't need to spend a whole lot of time here. But the reason I have it is because I really want these steps. I want them because they're exactly the same steps that we will use when we do polynomial long division. So we're going to divide, multiply, subtract, bring down or drop down it like I wrote it there, and then repeat until we're done. And so on the next board, we're going to do a long division problem. This is usually not very many people's favorite things. It's kind of messy. It's a bit of a disaster. It works, but it's just not real elegant. Some people like it because of the repetition in the process, but honestly, even I think they're just a little weird. So if you're out there and you like it, congratulations, lucky you. But this is definitely not my favorite thing, but it is useful, so we're going to do it. All right, so now we're going to do an example of long division. Before we do, I want to just mention briefly, because this is a pretty nice concept, the idea of a missing term. Basically, we need everything in a polynomial when we do long division from the highest power on down. So in this case, I have x cubed plus 6x plus 1, and it's pretty clearly missing an x, right? There is no plain x term in it. So I need to fill it in with a 0x before I can do any division with it. So you'll notice that I have that same polynomial divided by 2x plus 1. And when I set it up, hello, look at that mess. When I set it up, I put a 0 in place just to hold that. And it really is, it's just a placeholder, okay? So I think theoretically you might be able to get it right without the placeholder. In reality, I've never seen anybody do it. I've been teaching this math for at least 10 years. I'm not even sure anymore. It's been that long, but I've never seen anybody get it right without the placeholder. So please put in the placeholder. All right, so here's what I have. You'll notice that I have what looks like kind of like a division problem here, and then off to the side, I have a mess of scratch work. Okay, and I would really recommend that when you're doing these problems, split your paper in half, do the division problem on one side, and any scratch work that you need on the other side. It's going to help keep things neater and cleaner, and trust me, that's a really good thing here. All right, so I start by taking the first thing on the inside, the 8x cubed, and dividing it by the first thing on the outside. So I do 8x cubed divided by 2x. That little bit of division works out to be 4x squared, and it goes up top. I like to line it up with the like terms. That way when I get to the end of the division box, I know that I'm done. Just like with a regular division problem, now that I've divided, I'm going to multiply. I'm going to take 4x squared, and now I'm going to use all of the 2x plus 1. So I do 4x squared times 2x plus 1, which gives me 8x cubed plus 4x squared. Bring that back, and now I have to subtract it. This is really your key step. Most of the time, people who understand the long division and do a pretty good job with it, if they make a mistake, it's because they mess up the subtraction. I highly recommend distribute your negative into the parentheses, so I haven't done that yet. I'm going to do that. Change your minus to a plus and bring that negative into both pieces. Because if you don't, well, the 8 minus 8 usually works out okay, but it looks like 6 plus 4, which would be 10. And it's not. We're subtracting it, so it's really 6 and negative 4, which makes 2x squared. So please be careful with the subtraction. I can't stress that enough. So anyway, I get 2x squared, and then I drop down the 0x and the 1. Nice. Now we're going to do it again. I take the 2x squared, divide it by 2x. That gives me x, which I put up top. I multiply, I multiply the x times the 2x plus 1, which gives me 2x squared plus x. By the way, I recommend pausing this video frequently to try and keep up with me because I'm just kind of walking through this pretty quick. So I bring the 2x squared plus x back, and now I'm going to subtract again. Again, I recommend change it to a plus, change the signs. It's easier to get it right that way. 2 and negative 2 is 0, that's gone. 0 and negative 1 makes negative x. Down comes the 1. We still have x's left, so we're still dividing. Let's do it again. I take the negative x divided by 2x. That gives me a negative half. That's ugly, but it's fair game. Okay, there's nothing wrong with the fraction. So we get negative half. It goes up top. I multiply negative half times 2x plus 1 again, which gives me negative x minus a half. Again, change those signs. Change this to addition. Change those both to addition. In this case, 1 plus a half is 3 halves. And that's my remainder. But I'm going to write my remainder as a weird-looking fraction. So I get 3 halves. So notice I have a plus. 3 halves over what I was dividing by the 2x plus 1. So long division is kind of miserable. Most people really don't care very much for it. And I completely understand that. So spend some time on it. Get good enough at it so that you can do it. I'm definitely not promising you're ever going to like it. So there, that's long division. Let's do something nicer. All right, let's do synthetic division. This is way better than long division. So the first thing is, I just said it's way better. Why don't we use it all the time? Because it only works for a limited number of things. You can only do it, it only works when you're dividing by something of the form x minus c. So notice no powers on the x, right? No power here other than 1. No coefficient in front of x other than 1. It does work with a plus sign there, then c is just a negative number. So it's pretty limited. The last problem that we did had a 2x, right, one that we were dividing by. We couldn't have done it with synthetic division, as unfortunate as that is. So here's how it works. I have this problem, x to the 4th plus 3x cubed minus 4x squared plus 2, all divided by x minus 2. So it fits the bill. We're dividing by something that's just x minus a number. The first thing I need to know is that I'm going to set up this upside down box, and in front of it, I'm going to put the 0 of the divisor. So my divisor here is x minus 2. Well, ask yourself, what would make 0 if I plugged it in for x? And the answer is 2. Here's a hint. It's always the opposite of this number that you're looking at here. So we have a 2 there. And then notice that inside, I stole all the coefficients out of the thing I'm dividing. Now, one more thing. There's an extra number there, right? We have a 1, a 3, a negative 4, and then we have a 0. You cannot have missing terms here. It is absolutely impossible to get these right if you don't fill in any missing terms. So I'm just warning you, if you forget that 0, it's never going to be right for you. All right, so here's why this is so, well, actually, it should be we should all be able to come up with some reasons why this is already better. There are no x's, just numbers. And that automatically says, hey, this is a little different and hopefully a little bit better. All right, so here's how it works. We have the 0, the divisor out front, the coefficients on the inside. The first coefficient just drops straight down. So you'll notice I have another line down here. I bring the 1 down, it goes underneath that line. Now I'm just going to start a process of multiplying and adding. And that is beautiful because you're just multiplying and adding. And you have a calculator, so you can use that. So down comes the 1. I multiply. 2 times 1 is 2, and I put that up right underneath the 3. Now I add. 3 and 2 makes 5. Then I multiply again. 2 times 5 is 10. And I add. Negative 4 and 10 makes 6. And I multiply. 2 times 6 is 12. And I add. 0 and 12 makes 12. 2 times 12 is 24. 2 plus 24 is 26. And now we're done. We just have to write the answer. So look how nice that was. First number drops down, multiply, add. And just go all the way down the line and you'll have it. But here's what we have. The answer then to the division problem starts 1 degree lower. So I have 1, and since my original problem had x to the 4th, this is going to be 1x cubed plus 5x squared plus 6x plus 12. And guess what? That makes the 26 my remainder. Okay, so that's pretty fun. And that's synthetic division. So go and do a bunch of examples. You really, really want to get good at this. This is going to be super important as we go into the next couple of sections to help us find zeros of polynomials. And the reason for that is coming up in about just as soon as I change my board. All right, so here's why we're learning all this division stuff. Okay, our goal in this chapter, is really to figure out zeros for polynomials. And the bigger polynomials get, the messier that process becomes. And so what we have is that we have something called the remainder and the factor theorems, and they're going to help us out. So here's what the remainder theorem says. It says if a polynomial p of x is divided by x minus c, then the remainder is equal to p of c. Okay, so that might be clear as mud, so let me do an attempt to try and explain that just a little bit. First, I'll point out we're dividing by something that we could do with synthetic division, right? We have x minus c. That is synthetic division. And it says the remainder is equal to p of c. So if you plug in that divisor, right, we use the opposite. So we are going to use c here when we do our synthetic division. If you plug that in, you get the same remainder as if you plug in the number itself. And you're like, well, why can't I just plug 2 into the polynomial and see what I get? You could. But here's why. What remainder would be way more useful than any other? Well, generally when we divide, the remainder we would like to get more than any other is 0. What are we looking for when we solve our polynomials? We're looking for where they are equal to 0. So if we can find, either with synthetic division or in any other method, a 0 or with synthetic division that we get a remainder of 0, we just found a 0 for our polynomial. Even better, if we combine it with the factor theorem, which says x minus c is a factor of p of x if and only if p of c is equal to 0. If we combine it with the factor theorem, now what we've done, if you think about what just happened with synthetic division, it shrunk our polynomial down into a smaller polynomial. And we're going to basically use this process of find a 0, shrink the polynomial. Find a 0, shrink the polynomial. Because what happens, or what's going to happen with us anyway, is that most of the zeros we go looking for are pretty nice numbers, and we can find them and through a series of methods that we're going to look at in the next section, actually. But not all zeros are nice. We're going to see zeros that come out to have square roots in them. We'll eventually see zeros that have the number I in them. And none of our other methods are going to find those zeros. So what we do is we go through the remainder and factor theorems. We keep cutting our polynomials down smaller and smaller until we get to a quadratic. And then you can use the quadratic formula and find anything you want for those last 2 zeros. So anyway, that's the remainder and factor theorems. I'll bring them back up when we talk about finding zeros of polynomials in the next section. But until then, have a good day.